In this video we're going to talk about inverse functions and logarithmic functions and exponential functions. And in our discussion of inverse functions we'll also touch on inverse trig functions and the inverse trig that we could see in this course. So first we'll define the inverse function. Sorry, I heard a noise over there. Let's define the inverse function. Now, to define the inverse function, I'm going to introduce some notation. Now, this notation you will never be asked to reproduce on a homework or a test, but it's useful for helping to define and understand the definition of an inverse function. So, let's just start inverse functions. Inverse functions. Definition. So, a function, in its most basic sense, well, it has a domain and a range. It takes elements of the domain and maps them to elements in the range. So like f of x equals x squared, if you throw 4 into the domain, you'll get 16 in the range. So it takes domain elements into range elements. So let f be a regular function which maps some domain to some range. So f colon domain arrow range says f takes a domain to a range. Again, I'm not going to test you on the notation, but this is useful for defining an inverse function. So let f map a domain to a range, be a function. So as a function, it satisfies what the vertical line test. Now here's the inverse function. We're going to use this notation. F to the negative 1. We're going to call this f inverse. F inverse, to define f inverse, you need a regular function. F inverse does this same mapping except backwards. F inverse takes some range into some domain. Now, it doesn't just do this randomly. It must satisfy a property. So let f inverse map range to domain be the function which satisfies this. For which f inverse, I want to write the other one first because that's how I wrote it in my notes, which means that's probably how it's written in the book. For which f composed with f inverse is the same as f inverse composed with f. So remember, composition of functions, that's like that f of g of 3. So you put 3 into g, you get a number, and you put that into f. We won't see compositions, well, we will see compositions pretty much throughout the semester, but they're going to be not, well, knowing that they are compositions is not going to be all that useful, except for defining these. Where was I? Let f be a function, let f inverse be the function for which these are equal, but they also equal something else. They also equal just x. And I'll explain that a little. We'll see in an example what that means, and I'll explain something about what that means in a moment before we, well, after we finish this definition. Let f inverse be that function. We call f inverse of x the inverse function of f of x. Now, why do we call it the inverse function? Well, let me erase part of this board. I don't have to erase part of this board. Inverse in math is a very important word. It actually means something algebraically and with functions. Recall how do you solve this equation for x? 2x equals 5. How would you solve that for x? Well, many of you would say divide both sides by 2, and then you get, what, x equals 5 halves. There's another way of viewing that because division and multiplication are actually the same thing. We can multiply this entire equation by 1/2, and then that reduces to x equals 5 halves. Of course, that's the same as dividing by 2, but what I'd like you to observe with this is using multiplication. This 2 and this 1/2 are very conveniently related. They're conveniently related in that when you multiply them, you get 1. And that allows us, for example, to solve this. In math, when you have two numbers where you multiply them and you get 1, we call them inverse numbers. With functions, it's quite similar, except we're not going to multiply functions here. We're going to use a different operation than multiplication on these functions. We're going to use the operation known as composition. And the inverse function, just like with inverse numbers, is quite convenient under that operation. Now, what does that all mean? That's a reasonably complicated statement I just said. Let's see what that means in an example. Which example do I want? I want 3x plus 4. So let's erase the board and let's find an inverse. We'll do two things with inverse functions. First, we'll find inverses and use that to understand them geometrically. Then we will do inverse trig once we have a nice theorem on inverse functions. So this example will be to find an inverse function. Find f inverse of x given this function. Given f of x equals 3x plus 4. And to find f inverse of x, we're going to follow a procedure, an algorithm, with a couple of steps. There are a few different ways of describing this algorithm. Which way did I write down in my notes? Okay, I did this way. So there are a couple ways of doing this. They're the same algorithm. But to find f inverse of x for this function, we're going to first rewrite this f as just y. I think this might not look good if I just write it under there. Okay, step 1. Let's just say step. Y equals 3x plus 4. So just replace f of x with y. Step 2 will be to solve this equation for x. Well, right now it's solved for y. That's not the same as being solved for x. Here's x. That's not isolated. To isolate x, we need to get rid of the 4 and the 3. Well, let's get rid of the 4 first. So step 2 will be solve for x. Well, we got rid of the 4, now we have to get rid of the 3 to solve for x, and I'm going to write it on the other side. I'm going to divide this by 3 or multiply by 1/3, they're the same. And then I'm going to just write the x's on the left side. So x equals y minus 4 times 1/3, y minus 4 divided by 3. Well, right here we haven't found the inverse function exactly, but step 3 will be, with this computation, we can find the inverse function. So f inverse of x is this quantity with an x instead of a y, because we're taking x as our inputs for these functions. So here we have the inverse function. Step 1, replace f of x with y. Step 2, solve for x. Step 3, rewrite this piece that you solved for. Rewrite that with x's instead of y's. And that's your inverse function. Now, why is this the inverse function? Well, let's do a computation that shows why this is an inverse function. Did I write that down? I didn't write that down anywhere. Let's, why does this work, I guess I should say. Well, we can verify that this gives us the inverse function by using that composition definition. Well, let's check the definition. Recall this definition. This is the definition of the inverse function. Well, let's do these compositions and show that they're equal and they happen to equal just x. I'm going to do them on the first board. Now on your, there's one of these on the homework. You don't have to show that it works. You can just find it. You could check for yourselves that it works, but that's not part of your homework. So why does this work? Well, let's do the composition. F inverse composed with F, what does that equal? Equals. Well, what's F inverse? F inverse is X. Well, let's just rewrite this as this, with the this notation, before doing any substitution. F composed with F inverse is the same as, F inverse composed with F is the same as F inverse of F. Well, what's F of X? F was 3x minus 4. So F inverse with 3x minus 4 in it, 3x plus 4. F is 3x plus 4, so we want F inverse with 3x plus 4 as its input. Well, we input 3x plus 4 into this function. So we get 3x plus 4. Replace all x's here with 3x plus 4. So 3x plus 4. And then we still have the negative 4 and the 3. Well, now we just have to simplify this, and hopefully it'll simplify to x, because we need this to be x to simplify to x in order for this to be the correct inverse. Well, 4 minus 4 is 0. So the top is just 3x, the bottom is still a 3, and those 3's cancel. Well, that's half of the verification. We need the other half of the verification. We showed, what did we show? We showed F inverse composed with F was x. Well, that's this part. We also, if we are to verify this, need to show F composed with F inverse is x. So let's do that. I might need that portion of the board. Let's also check, maybe I should have written check, that it works. And let's check the other part of the definition. We want to show, in order for this to, in order to verify that that gives us the correct inverse, we need to show that this composition simplifies to x. Well, let's rewrite this as f of f inverse of x. So we take f inverse of x as our input for f. Well, f inverse was, what was it? It was x minus 4 over 3. So we're taking f inverse, inputting that into f. Well, f was 3x plus 4. So let's write it up here. Remember, f of x was 3x plus 4. So we're going to input here x minus 4 over 3. So we're going to replace all x's in this with x minus 4 over 3. 3 isn't an x. X is an x. That was is an x, not isn't an x. X is an x. So we're going to replace that x with x minus 4 over 3. and then we still need this plus 4. Plus 4 is not an x. So f of f inverse is 3 times x minus 4 over 3 plus 4. We input this for x. And now we just need to simplify this. There are a couple ways you could do the first step. I think the most convenient thing to notice would be that this 3 and that 3 cancel. If you multiply something by 3 and then divide by 3, that's the same as doing nothing, or multiplying by 1. So 3 over 3 cancels. You're left with x minus 4 and plus 4. Of course, the 4 and the negative 4 make 0. So right here, we've just checked that that inverse is correct by looking at the definition of the inverse. So notice we have all these numbers, 3 and 4, and positives and negatives all over the place. But these computations, these compositions we just did, all resulted in x. That's why this inverse is useful. And from that, we can actually get a nice visual, which we'll do right now by graphing f and f inverse. So on your homework, you don't have to check these compositions. You might want to at least check one of them, see how that goes. But let's graph these and figure out a relation. So with that same example, graph f of x and its inverse. Now, these are both lines. The first one is more obviously a line in this form because it's in the slope-intercept form. The second one is not obviously a line when it's written like this. But let's reduce this fraction. We can reduce that fraction by doing what? By doing one of these things. That wouldn't work the other way if it were 3 over x minus 4. Just this way. You can get rid of that. Now right here, this is also a line with slope a third, y-intercept negative 4/3. That has slope 3, y-intercept 4. The slope-intercept form is quite convenient if you're graphing lines. There's a good chance this is the last There's a good chance this is the last line we're going to graph this semester. Chance. So let's graph these lines on the same graph. I didn't write that, but on the same graph. Let's do it on this board. The first one, slope is 3, y-intercept is 4. So we'll say 4 is somewhere up there. Slope of 3 is reasonably slanted. I mean, slope of 1 is the, that line. Slope of 3 is a little more slanted than that. So here's f of x equals 3x plus 4. If you're taking notes, you might not want to write that function there just yet. I might move it depending on how the rest of the graph goes. But there's f of x. F inverse has y-intercept negative 4/3. That's somewhere below here. I'm going to try to be kind of close to scale in this example so that the geometry looks nice in a moment. So this up here is 4. 4/3 actually should be a little lower. 4/3, 1 1/3. That's a third of this length. So I'm going to try to draw that about a third of that length. So we have slope, or y-intercept negative 4/3. Slope is 1/3. So that's kind of slanted, but less slanted. And it's less slanted than slope 1. I'm going to extend this line a little more. something like that, and this is f inverse of x. And I guess I'll write equals what? X thirds, negative 4 thirds. Now, one thing you'll notice about these graphs, both of these lines look like they might share a property. That composition definition is reflected in this graph. Notice that these two lines that we drew are symmetric about the line y equals x. So if you fold your graph, or fold your paper over on y equals x, these two lines will overlap. And that's a convenient theorem. So let's write that as a remark. I'm going to erase this and then write the remark. 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 The graphs of f of x and f inverse of x are symmetric about the line y equals x. So if you need to find an inverse function and you have its graph, then all you have to do is reflect it across the line y equals x. Let's do one more example like this. This remark, by the way, is a geometric interpretation of that composition definition, or of the composition of inverse function definition. And what we're going to see next is that process I described for finding the inverse function doesn't necessarily always work. So let's say this process doesn't always work. And let's look at this example, and we will see two different ways in which it doesn't work. Those two ways will be the same way. One will be reflected algebraically, one will be reflected geometrically. So find f inverse of x for this function. Just x squared. So let's first try it algebraically, and we'll see what goes wrong. Step 1, replace f of x with y. Step 2, solve for x. Step 3, call this, with y's written as x's, f inverse of x. Now what's wrong with this? We went through this process, we solved, and we have something that can be written as f inverse of x. Now what went wrong with this? Well, you'll notice this right here takes x as its input, and then it throws out two different numbers as its output. A function can't do that. A function must not throw two different numbers out given an input. So right here, that process does not work on this function on its domain because it resulted in something that was not a function. One thing we can do, however, is restrict the domain so that we won't have to make this choice when inputting an x. Before doing that, I'd like to show this geometrically, what this means for it to not be a function, because it has a nice visual, especially because we have a visual for what it means for a graph to be a function. So right there, we showed that process wouldn't work on this function on its domain. Let's also show that it wouldn't work using the graphs. So let's say another way to find f has no inverse on its domain is using the graphs. Well, we know what f of x looks like. Here's f of x. And I'm going to draw the inverse on a different graph. With those lines, it was convenient to draw them on the same graph because it resulted in a visual observation. Here, I'm going to draw f inverse on another graph. Well, how do we find f inverse? Using a graph. We take the line y equals x, slope 1, y-intercept 0, and we flip this function over that line. So right here, this point at 0, 0 is going to be the same, but the rest of this gets flipped over the line. And what does that look like? That would look like this. So let's say this is f inverse of x. And let's put some question marks after that, because if we did this graph and if we did this graphically and got this, we would look at that and say, that's not a function. Why is it not a function? It does not satisfy the vertical line test. So let's say question mark, not a function. So either of those two ways, excuse me, I inhaled chalk. There's little ventilation in this room, because if I put a fan or something on, the microphone picks it up, and I'd rather you hear me than a fan. But one consequence of that is that I inhaled chalk. Maybe not inhale, maybe it's just caught in my throat. Okay, where was I? This right here is not a function. We showed that this inverse is not a function. But one thing we can do is restrict the domain so that this is a function. So what would that look like? So I'm still going to work with these graphs. I'll just redraw them. I'd rather have the entire chalkboard for the next part. What we have using the graphs is that f looks like this, and f inverse would look like that if it existed. But how can we want this to be a function. In other words, we want to remove where it does not satisfy the vertical line test. Well, there are a couple different choices. Well, there are many different choices. A couple choices that are probably more obvious than other choices. One thing we can do so that this is a function is get rid of that piece. Get rid of that piece. That satisfies the vertical line test. But how is that reflected over here? Maybe reflected wasn't the right word. Yeah, okay, reflected was actually the perfect word. How is that reflected in this function? Well, which piece did we flip over that resulted in down there? This piece right here. So right here, if we restricted the domain on a restricted domain. We restrict the domain, in this case, what, to 0 to infinity. But we restricted this domain so that when we flipped it over, we had a graph that satisfied the vertical line test. So using that, let's find f inverse of x on a restricted domain. Example. Same example as before. Find f inverse of x on a restricted domain for f of x equals x squared. And we're going to do this algebraically. We'll see in the algebra where we restrict the domain. Same process. Y equals x squared. Solve this for x. X equals positive negative root y. Right here is where we have to make a choice. We could choose the positive or we could choose the negative. I'm going to choose the positive because when we have a positive, we don't have to write anything. When we have a negative, we have to write something. So I'll choose the positive. And right here, I'll just write the positive to make it clear that I'm choosing the positive. But this is only on certain values. Right here, we have the positive square roots. So let's say for x in where? I might be going off the screen. For x in, we're taking only the positive square root, or 0. So we're going to restrict our domain to 0 to infinity. And doing that allows us to go to step 3 and say f inverse of x is just root x. This is now a function, and we have this domain restriction. Now, it might be useful, it is useful, to have a graphical reason for a domain restriction to exist. And let's do that. I'm going to rewrite this for x in that interval. In my notes, I wrote it a little nicer, but I think nicer. I mean, they're the same thing, of course. You might want to see that as for x greater than or equal to 0. Same thing as the interval. But let's look at the graph and figure out what we had to do in order to be sure that the inverse function exists. So what did we do on the graph? I didn't check the composition. The composition is just square roots squared cancel out. You didn't have to check it. I didn't write down to check it. What did we do in the graph with this example? We needed this to satisfy the vertical line test. Why did this not satisfy the vertical line test? Well, this didn't satisfy the vertical line test because vertical lines go through it more than once. But how is that reflected over here in the original function? We would like a condition on the original function that guarantees an inverse exists or doesn't exist. Well, what does this vertical line look like if we flip it across the line y equals x? It would look like a horizontal line. Flip that diagonally across y equals x. You get a horizontal line. So right here we notice a vertical line intersecting this graph twice corresponds to a horizontal line intersecting this graph twice. And that's a theorem. let's write it as a theorem. I want the phrasing the book used. This theorem is called horizontal line test. For a function f of x, I'm not going to write the of x, so I guess I'll be slightly different than the book. I mean, sometimes it's nice to have the of x. Sometimes the of x just gets in the way. For a function f, the inverse function f inverse of x exists if and only if every horizontal line if and only if every horizontal line intersects the graph of f no more than once. If and only if every horizontal line intersects the graph of f no more than once. Now, one thing I noticed I did not explain last week was with the vertical line test, so I'll explain it this week. This phrase in math, if and only if, means something. Right here we have something before if and only if, and something after if and only if. If and only if in math means that what is before it is identical, logically, to what's after it. In other words, this assumption implies this assumption, or this assumption implies this conclusion, and this assumption implies this. In other words, they're identical statements logically. And we'll interpret that to mean an inverse function will exist when every horizontal line intersects it no more than once, and if you have a graph where every horizontal line intersects no more than once, then the inverse exists. I'm not going to test you on that logic, but just know if you see if and only if in math, you might see that more if you take Calc 2, Calc 3. It means that this statement implies this statement, and this statement down here implies this statement, and from that they are logically equivalent. So an inverse function existing is the same as every horizontal line intersects the graph no more than once. And we can see that in the x squared example. In the x squared example, if we just looked at the graph, well, if we had this result, and we just looked at the graph, an inverse here doesn't exist because this graph does not satisfy the horizontal line test. But what you can do, what you can always do, is restrict the domain so that the horizontal line test is satisfied. Now let's look at the trig functions. And let's define the trig inverse functions. Now we didn't go over the graphs of the trig functions last week. Let's go over them now. First we'll do sine. Y equals sine of x. So right here I have two boards meeting, so that should be just a continuous line. But it's hard to make it perfect when you have to go over board, go over where two boards meet. So right here we have the graph of sine of x. Now let's mark off some points. Sine of x goes between 1 and negative 1. Maybe I'll write f of x equals sine of x, so you know which function this is. And you'll notice it starts repeating itself. So we have this piece of the graph, and then after that, it'll repeat itself. Before this, it does the same thing. Now when does it repeat itself? Sine of x repeats itself at 2 pi. Every 2 pi. That point happens at pi. This top point up here happens at pi over 2. This bottom point down here happens at 3 pi over 2. And if you go the other direction, this point right here would happen at negative 2 pi. This point here at negative pi. This point here, negative pi over 2. This point here, negative 3 pi over 2. Now, the first thing we'll notice about this is that this graph does not satisfy the horizontal line test. So if we want to define sine inverse, which we do want to define sine inverse because we're going to use it, we would need to restrict the domain so that this does satisfy the horizontal line test. There are many choices of the domain restriction. It's standard to choose one of them, and we will stick with that standard choice. So we'll say, well, I said it out loud, does not satisfy the horizontal line test, but it does if we consider only this piece. From down there to up there, our goal is to define the inverse sine function, which means we need a piece on which the horizontal line test is satisfied, and we would like it to, where's that? And we would like to also hit all values between 1 and negative 1. Right here, that hits all values between 1 and negative 1, and it satisfies the horizontal line test. So I'll say f satisfies horizontal line test here, in this shaded in portion. In other words, if we restrict the domain to pi over 2 to negative pi, or sorry, if we restrict it to negative pi over 2 to pi over 2, then it'll satisfy the horizontal line test. So let's formally define the inverse sine function. We'll remember we're using negative pi over 2 to pi over 2. We're including the endpoints because we also want it to hit 1. To define sine inverse, there. To define sine inverse of x, which we'll write like that with the negative 1 there. To define sine inverse of x, we restrict the domain on sine of x. And what does that look like? Well, remember, we're taking the domain to just be negative pi over 2 to pi over 2. That's our domain restriction. The actual domain of sine is everything, but we're restricting the domain. Given this restriction, the range is negative 1 to 1. And sine inverse of x then flips these around sine inverse x takes negative 1 to 1 to negative pi over 2 to pi over 2. And with this definition on this domain, it would satisfy that composition relation. I'm not going to write that down, but it does satisfy the composition. Just like with trig functions, we wanted to evaluate trig functions at numbers, at certain numbers, at angles. We're going to want to evaluate inverse trig functions at certain numbers. Now, a couple key observations to make about that. This domain restriction Negative pi over 2 to pi over 2. Let's go back to this diagram. Negative pi over 2 is the angle down there. Pi over 2 is the angle up there. And sine of x we restricted to being between negative pi over 2 and pi over 2. In other words, the only inputs in here that we're using to define inverse sine are in quadrants 1 and 2. Jeez. These are not quadrants 1 and 2. Are in quadrants 4 and 1. In other words, so remark, in order to define inverse sine, the only inputs on sine are quadrants 4 and 1 angles and the axes. So the only outputs for inverse sine, are angles in quadrants 4 and 1, and the axes. So I'll say and axes. Let's say and some axes. In this case, negative pi over 2, 0, and pi over 2. And one other observation we'll make is that sine is positive up here. Sine is negative down here. So if we're taking as an input a positive number for inverse sine, the output will be in quadrant 1. If we're taking in a negative number for inverse sine, the output will be in quadrant 4. So let's do a couple examples of that. And we'll keep this remark in mind. Example. We'll do 2 examples. Inverse sine of 1 over root 2. Now our immediate observation, this is a positive number. So our answer will be in quadrant 1. We know this is going to be in quadrant 1 because it's inverse sine of a positive number. Now we just have to figure out which angle in quadrant 1 this takes as, remember, trig functions take angles as the input and throw out numbers. Inverse trig functions are going to take numbers and throw out angles. Now to figure out which angle, I again like to go back to those triangles. This triangle, the pi over 6, pi over 3, pi over 2 triangle, with sides in that ratio, and the pi over 4, pi over 4, pi over 2 triangle, with sides in that ratio. And then I look at these numbers and figure out which triangle has those numbers. Well, this is a 1 and a root 2. There's no root 2 there. There's a root 2 there, and there's a 1. So we're going to use this triangle to find our answer. We're going to use that triangle. Maybe I'll write it over here. Might be nicer if I write it over here, since the answer is going to be up there. Remember, sine is opposite over hypotenuse. Here, we want the opposite over hypotenuse to be 1 over root 2. Well, we can use this angle. We can use the other one, they're the same. The opposite is 1, hypotenuse is root 2, so we get pi over 4. And we want that in the first quadrant. Pi over 4 is in the first quadrant. let's do 3 examples actually. Let's do this example next. Example. Sine inverse -1 over root 2. What does this equal? Well, let's, again, before we draw the triangle, let's make the quadrant observation. This is a negative number. By that remark, this answer is going to be in quadrant 4. By that remark. Well, which angle in quadrant 4? Again, we go to the triangles. We did this one before, so we know that it's going to be related to this triangle and not the one with the root 3. Opposite over hypotenuse, we want to be 1 over root 2 in quadrant 4. That takes care of the negative. So we again get pi over 4. But pi over 4 is that angle. That angle is not in quadrant 4. That angle is in quadrant 1. We want this to be in quadrant 4. We want it instead to go down into quadrant 4. Well, we want this to be pi over 4, that distance. So we want that angle to be negative pi over 4, because we're going down instead of up. We went down, so we have a negative angle. And we get negative pi over 4. So notice here for sine, you kind of get that the negative goes with the other negative. That generally works for sine. The next example we'll do with inverse sine is to find the inverse sine of 1. The angle whose sine is 1. Now, just like with the regular trig functions, if something wound up on an axis, you would not use a triangle argument. And here with the inverse trig functions, if we have 0 or 1 as our input, that would correspond to a point on an axis on the unit circle. So there are a couple ways you could find this out. I think the easiest way is to label the unit circle. And remember the domain restriction. So these 3 points on the unit circle are given by these ordered pairs. We want the angle whose sine is 1. Remember, the y-coordinate gives you sine of the angle. So where is the y-coordinate 1? Well, the y-coordinate is 1 up here. So we would want that angle as the output. That angle, remembering our domain restriction for sine, is just pi over 2. 5 pi over 2 is incorrect, because that is not part of our restricted domain. So we have just pi over 2 when we have the inverse sine of x. Let's next define the inverse cosine function. To do that, we would need the graph of the cosine function. So here's the cosine function. It looks quite similar to sine. I'm going to go a little farther over here. It looks quite similar to sine, except it's actually shifted over a little bit. And instead of starting at 0, 0, it's going to start up at 0, 1. Because cosine of 0 is 1. And this bottom point is negative 1. Just like sine, cosine's between 1 and negative 1. Just like sine, cosine starts repeating itself after 2 pi. And of course, back here, that'd be negative 2 pi. And then the relevant points for cosine, this bottom point occurs halfway, that occurs at pi. This intersects the x-axis at pi over 2. This intersects the x-axis there at 3 pi over 2. And similarly over here, this bottom point, negative pi over 2, negative 3 pi over 2. I'm about to sneeze. Okay, the sneeze went away. Now, again, we want to define the inverse cosine function. So we want to restrict our domain so that it satisfies the horizontal line test. Just like with sine, there are many domain restrictions you could use. But the standard one to choose, and the one we will choose, is this piece. On that piece, it hits everywhere between -1 and 1, and it satisfies the horizontal line test. Notice here, we're restricting it to 0 to pi, and we're including the endpoints again because we want to hit 1 and -1. So let's formally define the inverse cosine function. So cosine of x, I should start it like I did before. To define cosine inverse of x, we restrict the domain of cosine x. And we do that like this. Cosine x, we restricted to 0 to pi. And we got as our output -1 to 1 again. And with that, the inverse cosine of x flips these around. It takes numbers as its input and throws out these angles as its output. Now, the inverse sine threw out quadrants 1 and 4 angles as its output. Right here, we don't have quadrants 1 and 4. Where are 0 and pi? Well, where is the interval 0 to pi, I guess I should say. Well, let's look at this ASTC thing. 0 is there. Pi is there. We're restricting the domain of cosine to be 0 to pi and everything in between. So we get for inverse cosine quadrants 1 and 2. And we'll write this as a remark, just as we did before. Remark. Remark. The domain of cosine x is restricted to angles in quadrants 1 and 2. Angles in quadrants 1 and 2. And the axes. So I'll say again, and axes. Now, we're in quadrants 1 and 2. Cosine is positive in quadrant 1. Cosine is negative in quadrant 2. So that means if you take a positive as the input for inverse cosine, you'll get an angle 1, or a quadrant 1 angle. If you take a negative as your input for inverse cosine, you'll get a quadrant 2 angle. And we'll see that dealing with those quadrant 2 angles is a little different than in sine. So let's do a couple examples. keeping this remark and the domain restriction in mind. I think I wrote down the example I want to do over here. Yes, let's do these two examples. Example. Find the inverse cosine of root 3 over 2. Now, before doing anything, we're going to observe this is a positive number. It's not on any of the axes. In other words, it's not 0 or 1. It's a positive number, so that tells us our answer. Well, we knew before our answer would be in either quadrant 1 or quadrant 2. It's positive, so our answer is in quadrant 1. And now we need a triangle. We have a root 3, so we'll use the triangle that has a root 3. Pi over 6, pi over 3, pi over 2. Has sides in those ratios. And we want cosine to be root 3 over 2. Well, remember, cosine is adjacent over hypotenuse. For angle pi over 3, adjacent's 1, hypotenuse is 2. So that won't work. But for angle pi over 6, adjacent is root 3, hypotenuse is 2. So we get pi over 6, which is in quadrant 1. So now let's do this example. Now it would be quite convenient if, like sine, this answer were just negative pi over 6. But that's not the case. Why is that not the case? Well, for starters, negative pi over 6 is in quadrant 4. Cosine's positive in quadrant 4. That's not a positive number. What we can do is look at our domain restriction. We restrict the domain to quadrants 1 and 2 for cosine in order to define inverse cosine. Right here we have a negative. Cosine is negative in quadrant 2. So we know our answer is going to be in quadrant 2. And again, we're going to use this triangle. Pi over 6, pi over 3, pi over 2. 1 to root 3 to 2. And adjacent for pi over 6 is root 3. Hypotenuse is 2. So we get pi over 6. But how do we get that in quadrant 2? Well, how could we get that in quadrant 2? Why does this triangle argument work? Well, this would work. The triangle argument works when that's pi over 6. Well, this right here is pi over 6. That's not how we measure angles. We measure angles like that. So right here, this angle is in quadrant 2. What is that angle? What is that angle? Well, this piece is pi over 6. The straight line is pi. So if this whole thing is pi, and that's pi over 6, the arc we want is pi without pi over 6. Well, pi without pi over 6 is what? 6 pi over 6 without pi over 6. 6 and negative 1 make 5. So we get 5 pi over 6. And that's a phi. So right here, we have a different phenomenon for cosine inverse. That should be a little closer. And I was avoiding the break in the boards. So right here for sine, when you threw a negative on it, you could just throw a negative on your answer. For cosine, you can't do that because of the domain restriction. I mean, it would just be pi minus whatever that one is, I guess, in general. And similarly, we're going to define the inverse tangent function. And we'll start, again, with the graph of the tangent function. Tangent looks like this. And it has horizontal asymptotes. Vertical asymptotes, excuse me. At negative pi over 2 and pi over 2. So the first thing you'll notice, this goes through the origin. First thing you'll notice is that tangent exists in an interval of length pi. Negative pi over 2 to pi over 2. Well, one piece of it exists in an interval of length pi. And then it starts repeating itself. So with sine and cosine, which repeated itself after 2 pi units, tangent is going to repeat itself every pi units. And then if this is a length pi, from pi over 2, another length pi over would be 3 pi over 2. And then it goes in the negative direction as well to negative 3 pi over 2. Like that. Now, again, this function, tangent of x, does not satisfy the horizontal line test. But it will if we restrict the domain. Now, this domain restriction is going to look a little different. We'll restrict our domain so that what we get is that piece. In other words, we'll restrict our domain to negative pi over 2 to pi over 2. That'll hit all of our y values, and it will satisfy the horizontal line test. Now notice this function's not defined at pi over 2 and negative pi over 2. So instead of a closed interval, we're going to use an open interval in our restriction. So to define inverse tangent, we restrict the domain of tangent. And in this case, we'll restrict it to just negative pi over 2 to pi over 2. Now we're not including the endpoints because those are not in tangent's domain to begin with. Tangent is not defined at the endpoints. Now tangent is different. Tangent's not between just negative 1 and 1. Tangent hits all real numbers. That might be off the screen. I'm just going to rewrite this. Negative infinity to infinity. Tangent hits all real numbers. With this restriction, the inverse tangent of x then can take in any number, and it will send out angles between negative pi over 2 and pi over 2, not including the endpoints. Now, which quadrants are these in? Well, just like sine, the inverse tangent is going to be in quadrants 1 and 4. So let's draw that. Maybe I shouldn't have erased that last line. Well, that's okay. If you're taking notes, it's in your notes. The inverse tangent is restricted to negative pi over 2 to pi over 2. Well, negative pi over 2 again is down here. Pi over 2 is up here. And it's everything in between. So again, we're in quadrants 1 and 4. So remark. The outputs for inverse tangent of x are in quadrants 1 and 4. And we're not including the any of the y-axis because that's not in the domain of tangent, but it could also be in the positive x-axis. So I'll say and positive x-axis. So just like with sine and cosine, well actually just like with sine, similar to cosine, if you take a positive number as the input for inverse tangent, your answer will be in quadrant 1. If you take a negative as your input for inverse tangent, your answer will be in quadrant 4. Unless it's 0, in which case it'll be the positive x-axis, which is angle 0. So let's do an example of inverse tangent, with inverse tangent. Let me see which one I wrote down over here. That's a good one. Let's do the inverse tangent of -1 over root 3. Now, before we do anything, we use that remark and we observe that this is a negative number. So our answer with inverse tangent of a negative number is going to be in quadrant 4. So we know immediately, since it's negative, it's in quadrant 4. Well, now we need a triangle argument. We would like the triangle with root 3. So we draw this triangle, pi over 6, pi over 3, pi over 2, with sides in ratio 1 to root 3 to 2. And what is tangent? Tangent is opposite over adjacent. Opposite over adjacent. So we want opposite to be 1. We want adjacent to be root 3. And the fourth quadrant will take care of the negative. So we want opposite to be 1. We want adjacent to be root 3. The opposite of pi over 6 is 1, and its adjacent is root 3. So we know this is going to be pi over 6 in the fourth quadrant, which instead of going up, pi over 6, we want it in the fourth quadrant, so we'll go down pi over 6, which means the angle is negative pi over 6. Now, with these inverse trig functions, you can actually combine regular trig functions and inverse trig functions in these computations. So let's look at one example of this. Let's see how this example goes. Example, inverse sine of cosine of 2 pi over 3. So we want inverse sine of cosine of 2 pi over 3. Well, let's first find cosine of 2 pi over 3. Well, that's the standard trig argument. So let's say that this equals, what, sine inverse of something. We're going to find that something on the side. That something is cosine of 2 pi over 3. Well, 2 pi over 3 is in quadrant 2. How do you know it's in quadrant 2? Well, 2/3 is between a half and 1. So that's in quadrant 2. Cosine in quadrant 2 is negative. Sine is positive. Cosine in quadrant 2 is negative. And which number? Well, we need the triangle with a 3 in the denominator of one of the angles. So which triangle is that? We'll use the pi over 6, pi over 3, pi over 2, with sides in ratio 1 to root 3 to 2. Cosine of pi over 3. Cosine is what? Adjacent over hypotenuse. The adjacent is 1, hypotenuse is 2, and since that's a quadrant 2 angle, we get a negative. So we wanted the inverse sine of cosine of something, we found cosine of something, and now we need the inverse sine of negative 1/2. Inverse sine of negative 1/2. Well, how can we do that? Well, we do that just as we did before. Our first observation is that it's a negative number. So our answer is going to be in quadrant 4. So I'll just write as an aside so that we remember it later. We want this in quadrant 4 because that's negative. Well, now we need a half. We need sine of an angle to be a half. Sine of an angle to be a half. Well, this triangle has a 1 and a 2. There's a 1 and there's a 2. Sine is opposite over hypotenuse. 1 is opposite this angle. And the hypotenuse is 2. So we have the opposite is 1, the hypotenuse is 2. So we get pi over 6. But we want that in quadrant 4. So instead of going up into quadrant 1, we'll go down into quadrant 4. And we get negative pi over 6. Now these inverse trig functions, they do take a little bit of practice. So try the ones on the worksheet. See how they go. Let me know if you have questions. I'll have office hours on Tuesday of this week, assuming you watch this video before Tuesday, I guess. If you watch it after Tuesday, my office hours would be next week on Tuesday.